These are actual real images from the Cassini spacecraft as it orbits the planet Saturn, 10 times further from the Sun and from us than we are from the Sun. These are the rings. They're made out of dust and various size rocks, from meter size to dust size. And this is a little moon that influences on the rings. It pulls on the ring. It makes this kind of structure. You see the rings have this kind of, and that's because you have a little moon there. The gravity is pulling the dust and the particles as it orbits. This is not a simulation. Instruments measure different parameters, like the radio science. Okay, these are little swirls that you see in between the rings. Now this is Titan. Now notice the edge of Titan is very fuzzy, and the reason it's fuzzy is the same reason that the Earth's edge is fuzzy. It's because it has an atmosphere. But Titan has a much more extended atmosphere than the Earth. Goes out much further relative to its diameter. This is surface structure on the they have different names, cat scratches. There's a lot of haze. As I said, it's a very hazy planet. You can see Saturn when you look through it. And then the South Pole, that's where the pole, we have all these lakes. The lake I showed you was from the polar region. See how fuzzy Titan is? Because of the thick atmosphere, it's very dense. Its pressure is 1.5 times that of the Earth at the surface. And there's some kind of a spot there, like a hot spot. And it has structure look like rivers that kind of flows and look like basins of a lake or lowlands. This is the landing. Once the probe landed, it took this image. It's quite incredible. This is again, Saturn is all gas, so all these features you see are storms, really. And this looks like a mock-up. I mean, it doesn't look like a real planet. Unlike Jupiter, Saturn has a very uniform appearance, except for local storms. Jupiter has all this structure, but Saturn looks very, very flat. It's not as interesting, maybe. This is Dion, a small moon, and it has these very strange markings. A lot of these have been hit by other objects, by asteroids, and you see a lot of the structure that you see. This is an impact crater. Something hit right here. It looks like an eyeball. And at some time in the past, there was an impact by another object. And you see this. There's an interesting rift. It looks like a straight line all around this planet. Like somebody cut it in half, or wanted to cut it in half. Here's another eyeball, another impact crater that had created this huge structure. And then you have this white and dark stuff. The fact that we get this data, I don't know about you, but for me it's amazing. I had hard enough time to take a picture of my backyard. I want to see where else can we look for Earths, because we really haven't found one in our own solar system. It's all interesting, but so what? Well, the habitable zone. The habitable zone depends on how far you are from the source of heat, the star, and how big the star is and how much energy the star emits. So if you have a huge star, it's so hot, you've got to be far away, otherwise you get no liquid water, you get gas. So you look for small stars. When a small star, you can come much closer. So the habitable zone depends on the size of the star. Proxima Centauri is a star that's actually pretty small. It's actually pretty close to the Earth. It's only 4.2 light years away. And it should have planets. Now, why do you want to look close up? Because when you look close up at a planet that's close to the star, its effect on the star, different effects, but its effect on the star is much more pronounced. If you have an object that's very far away, you can't really look at the effect of the star, of the planet on the star, whether it's the star's wobble, or the star's rotation, or the fact that it goes in front of the star and blocks the light from the star. See, this is a sister galaxy to our own. It's not the closest one, but it's 2.5 million light years away. So that's 1 light year you travel this distance, 5.9 trillion miles. So the distance is this thing here, 18 zeros and a 4. To get to this galaxy, forget about getting to a star. So, but as Carl Sagan once said, there are billions and billions of stars in every galaxy. And in fact, there are billions of galaxies. Remember I talked about Doppler shift? The fact that there's motion, you can detect motion by the difference in frequency or changes in the frequency of light that emanates from the source. Well, that's how the first 321 plus planets around other stars were detected. And what they did is they looked at light from the star, compared it to a reference transition, a frequency that's very well known of iodine, and they monitored the difference in frequency between the fixed reference and the light coming from the star. And they found, if they observed for a long period of time, let's say a year, 2 years, that the frequency changed. It oscillated. So what happened was, if the planet, the same is true of our own star on the sun, Jupiter pulls on the sun. So it has an effect. So the sun doesn't rotate on its axis, it wobbles like this because of the pull of the planets. And the same is true of other planets, especially planets that were detected. Because we can't detect planets like on this Earth yet, but we can detect what's called hot Jupiters. These are guys that can be several times bigger than Jupiter, 10 times bigger than Jupiter, but they're close. So its orbit, Jupiter's period, is 12 years or 11 years around the sun. Earth's period around the sun is 1 year, right? These guys rotate their star at days or weeks. And those are the ones we can measure. Because if you wait if it's 10 years to do one cycle, it would take us, 30, 50 years to make one measurement. But so most of these that were detected are very close-in planets and very large planets that have a significant effect on the star. But that's not what we're interested in. We really would like to see, by the way, this kind of detection is very, very powerful. There are other ways to detect, and I'm not going to go into them. But what we'd like to see is Earth-like planets. We don't want to see them. We have 350 planets already. Who cares? I mean, they're big things. They're all gas, and they're hot. They're not hospitable at all. But we want to have Earth's planet. Well, how else would you detect planets? Well, the other way, as I kind of mentioned it, is transit. The planet orbits the star, and if the planet comes and blocks the sun or the star, and you're looking at this light, you see a decrease in light, and then it reemerges when it comes out on the other side. So that's the primary eclipse. And from this, you can get some information about the physics, the size of the planet, for example. Because you have an idea of the size of the star, you get a size of the planet, you can get some mass information, you get orbital information because you know the period that it does this, because this does this periodically. You can't do this in one measurement. You have to make 100 measurements or more. That's why only the short period planets are the ones that are most likely to be detected. But then you have the secondary eclipse. Now the secondary eclipse is actually even more interesting, because the secondary eclipse, you measure energy with the star, with the planet over here and the star. So you're looking at the energy of the star and the planet, and then the planet goes behind the star, and so you just got the star. So if you take the difference, what is the difference? It's the real signal from the planet. So that's a real detection of a planet as opposed to the oscillation, which is an indirect detection.